So L equal to summation I equal to 1 to n cross Q is a constant of motion. Anything else? Well, if I give you special forms of V, then of course you'll start discovering constants of the motion. In particular, if this thing here is a sum of two body forces or something like that, then it's harmonic forces or something, then the system is integral. No problem. But arbitrary V, there are not too many more constants of the motion. This came about because of rotational invariance of the whole system. This came about because of translational invariance of the whole system. This came about because of time translation invariance of the system. It's autonomous. Now there's one more. In Galilean mechanics, you can always boost to another frame of reference which moves with a constant speed, velocity with respect to the first. And that gives you 3 more constants of the motion. Which is this. It's exactly the same thing that I did in one-dimensional motion. Capital R is the coordinate of the center of mass of the system, center of momentum of the system, and capital M is the total mass of the system. In the relativistic case, you would have to impose not invariance under Galilean transformations, but Lorentz transformations, and then of course you would have the center of energy rather than the center of mass, but it's pretty much the same. These are the constants of the motion. How many are there? Well, it's 1 plus 3, 4 plus 3, 7 plus 3, 10 constants of the motion. This generates, this is the infinitesimal generator of time translations. This is the infinitesimal generator of space translations. This is the infinitesimal generators of rotations. And that's the infinitesimal generator of boosts to other frames of reference. They're all infinitesimal generators, they're constants of the motion. But this one, this set is explicitly time. And these are the 10 Galilean invariants. But our phase space is 6n dimensional. We need to find 6n minus 1 of them, or 6n in extended phase space. We have a measly 10. So it's immediately clear that it's not integrable. This sort of system is not integrable. If you don't give me more symmetry properties here, you can't find enough constants of the motion. There's not enough symmetry in the system, and generically it's not integrable. And generically this system is chaotic.
I don't understand the significance of time-dependent constants.
Well, it's not that. They are constants of the motion. They're sitting there. The interesting question is, what do these constants of the motion actually mean? Time-dependent or independent? What do they actually do? You're familiar with Noether's theorem, which says that when you have a continuous symmetry, then there exists a conserved quantity, or conserved current actually, but then a conserved quantity associated with it, which in this kind of mechanics translates to constants of the motion. Now, that's one aspect of it. But the deeper aspect is that this constant of the motion acts as the infinitesimal generator of the group of transformations under which the dynamical equations are invariant. In other words, the solution space gets mapped to the solution space. That's what dynamical symmetry means. Now, some of those are kinematic, and some of those are really dynamical symmetries. In this case, these are all kinematic symmetries. They follow independent of what this V is. No special role or anything. But there are other cases where you have extra symmetries which would depend on what the form of the V is, and those would lead to what's called hidden symmetry or dynamical symmetry. And we will talk a little bit about that too. But typically this is all that happens. There are only 10 Galilean constants of the motion, because this system is invariant under the Galilean group.
Yeah. So for n equal to 1, these all...
But yeah, n equal to 1 is a trivial case, right? This is simply a potential, and if it's a central potential, then I know how to integrate the system. It's integral. Pardon?
Pain constants of motion.
Yeah.
But
Let me say that. I mean, for 1 degree of freedom, capital N is not the same as little n. This is the number of particles.
Yeah.
Capital N is the number of dimensionality of the phase space. So even if you had, yeah.
So for arbitrary any kind of this kind of Hamiltonian, you
Yeah.
can say this 10 Galilean invariant
Yes.
will be there, and those come out from the symmetry of the system.
They come out from my postulated, from the Hamiltonian,
System,
which I wrote down based on the fact that it should be sphericalism and rotationalism invariant, it should be translation invariant, etc.
So those independent of potential, they will be there, right?
Yes, that's right. And that's not enough to integrate the system. So such a system is chaotic. What's interesting about let me just complete this. What's interesting about a Hamiltonian system is that if it's not integrable, it's chaotic. That is not true of dissipative systems. There are all sorts of intermediate behavior, as we'll see, but in a Hamiltonian system, if it is not integrable in a very specific sense, then the statement is there exist initial conditions for which the motion is chaotic. What's the set of initial conditions for which this happens? What's the measure of the set among the set of all possible initial conditions is a different question. There is in fact a very gradual progression as the system goes from integrable to non-integrable by changing some perturbation or something, that it starts off by a few initial conditions becoming chaotic, leading to chaotic motion, to finally, globally, no matter what initial condition you have, the system is chaotic. So there's from local, on complete integrability to complete chaos. This is possible. But the interesting thing is that for a Hamiltonian system, classical Hamiltonian system, if you do not have integrability, then there exist initial conditions for which you have chaotic motion immediately, in a very specific sense of chaos.
So what this same constant of motion is giving in this problem we were talking about?
Pardon, what's the?
But these same constant of motions we are getting.
They generate the symmetries. They generate symmetries, and what's meant by a symmetry of a Hamiltonian system? It means that you have a canonical transformation because it preserves the Hamiltonian structure of the system, such that the Hamiltonian does not change, so that the solution space is mapped onto the solution space. And these fellows will act as the generators in this case. Yeah.
So we started with dynamical systems and now we are discussing Hamiltonian systems.
Yeah. Which is a special case of dynamical systems.
So there exists dynamical systems for which there is no Hamiltonian.
Yeah. The only information I have on some general grounds is Hamiltonian systems. That's the one that's of interest to me in, for instance, in equilibrium statistical mechanics. I assume there's always a Hamiltonian. And there are, of course, serious dissipative systems where there's no Hamiltonian at all. We'll study them in some depth. Yeah. Pardon me? Greater than? No, the phase space dimensionality already, if n is 2, is 12 dimensional already. It's very high. So in fact that raises a good question. How soon does chaos occur? Well, it occurs very soon. Let's take motion in 2 dimensions. We take motion in a 2-dimensional plane, and let's make it bounded motion, because I don't want to have, I'm going to define chaos more precisely, but I don't want some exponential divergence simply because the phase space is unbounded. That's a very trivial kind of divergence. So phase space would be bounded and so on, or motion occurs in some bounded region of phase space. Let's take a carom this kind. So it's a square in which I put a particle in and give it some initial velocity, and the rule is that when it hits the wall is a perfect reflector and it undergoes specular reflection by the laws of reflection. Then this is a system with 2 degrees of freedom, x and y if you like. And there are 4 phase space variables, px, py, x and y. Then in this 4-dimensional phase space, the question is this system integrable or not? And it turns out the answer is yes, it's integrable. This is called, this is the most trivial example of a stadium problem. It's a Hamiltonian system. And I'm going to jump ahead and assume that you already know the criterion for integrability of a Hamiltonian system is that if it has n degrees of freedom, little n degrees of freedom, there must be little n constants of the motion in involution with each other, functionally independent and in involution with each other. So as soon as I find two of them, the job is done. There are two constants of the motion here. What would they be? Well, it's a free particle. It's a free particle inside here. And the constraint that it stays inside here is a non-holonomic constraint, because it just says, if this is L and 0 and L, it says 0 less than equal to x, y less than equal to L. So this is not an integrable constraint. So it's not going to decrease the number of degrees of freedom at all. Just an inequality. So there is still a 2 degrees of freedom, 4-dimensional phase space. But there are two trivial constants of the motion in this problem. And what are they? Well, this undergoes perfect reflection. Doesn't lose its energy at all. Right? So what are the constants of the motion? At any collision with this wall, the momentum is reversed. So a collision with a wall parallel to the x-axis reverses the direction of the y momentum. So what are the constants of the motion? Not px and py. Px squared and py squared. Not mod px and mod py. Although they are constants of the motion, they are not analytic. So I'm looking for differentiable constants of the motion. So I'd say px squared and py squared are constants of the motion. Two constants of the motion. They're independent of each other. The Hamiltonian is just the sum of these two guys. So it's not a third constant of the motion, apart from some mass or something. Now, you could ask, what happens? So we're guaranteed by this Liouville-Arnold theorem that this is an integrable system. It's trivially integrable as it stands. So if you give me any initial condition, in principle I could tell you arbitrarily long into the future where the particle is going to be. Except for sets of measure 0. Sometimes the initial momentum could be directed so that it hits this corner. We will then assume that there's a pocket and the particle disappears. Because that's a set of measure 0, and this is really a pseudo-integrable system in that sense. So at the corner you have to specify it's not a smooth boundary condition. So except for that, it's integrable. Two constants of the motion. It's integrable. Now, suppose instead of a square, I had some other shape. I had this thing. A circular billiard, a circular stadium. I put a particle in there, and it bounces off in exactly the same groove. Is this an integrable system? You need to tell me two constants of the motion. So, I do know one of them is this. Px squared plus py squared. But you have to show me another constant of the motion. This is the origin in the center. Pardon me? It's got circular symmetry. This problem has zero potential inside, but it has infinite potential on and outside the boundary. And that's a circularly symmetric boundary condition. So there is circular symmetry. V of r is 0 for little r less than a, and V of r is infinite for r greater than equal to a. Pardon me? The angular momentum, there's no third dimension. There's no third dimension in this problem. There's no third dimension at all. So you're right, it's angular momentum, except the angular momentum in this problem is a scalar. In 2 dimensions, the angular momentum is a scalar. Right? So after all, what's the angular momentum? It's epsilon ij k xj pk in 3 dimensions. In 2 dimensions, it's just xpy minus ypx. That's all it is in 2 dimensions. xi with this epsilon factor. Epsilon 1, 1 is equal to 1, 1, 1 is 0, 2, 2 is 0, 1, 2 is plus 1, 2, 1 is minus 1. So it's a scalar. Is the angular momentum in 2 dimensions a scalar? No. Yes. There's no third dimension. It's only 2 dimensions. So can I assert that the angular momentum transforms like a scalar? Pseudo-scalar. So under x goes to minus x, y goes to minus y, is this going to be change sign? Huh?
Because x and p both will change.
Is x goes to minus x, y goes to minus y an improper transformation in 2 dimensions? R goes to minus R. Is that an improper transformation? Well, the Jacobian of this transformation is minus 1, 0, 0. I mean, the Jacobian matrix is this. That's got determinant plus 1. That's a rotation. Yeah, it's a rotation about pi, right? So this is x, this is y. And it's inverted to look like this. So in an even number of dimensions, parity is not an improper transformation. There's a big difference between rotations in an even number of dimensions and an odd number. Huge difference. That is why the Lie group properties are totally different for SO2n and SO2n plus 1. It's a big difference. So x goes to minus x, y goes to y. That's a parity. This reflection about the x-axis or the y-axis. Those are parity transformations. And under those, this thing will change sign. This epsilon integrals. So that is indeed a constant of the motion. So there's a second one, which is L, which is xpy minus 1. This is a constant of the motion. And it's functionally independent of h. That's it. So immediately you have integrability by this criteria. This system is integral. Now, let me take both these fellows and combine them together. So in this, I'll put 2 particles instead of 1, and they can undergo elastic collisions with each other in between. Then the system becomes immediately chaotic. In fact, I'll go better than that. I'll say instead of a second particle, let's just put a fixed scatterer in between. Let's even make that a little big and put an obstruction here which is circular. And I put a single particle inside. This system is chaotic. Alright. So you have 2 degrees of freedom. This particle has 2 degrees of freedom, x and y. It's got this circular obstacle whose circular symmetry is not compatible in some sense with the square symmetry of this boundary. And this system becomes chaotic because there are a whole lot of trajectories for which it won't. This fellow will bounce back and forth. There are a whole lot of trajectories for which this guy will bounce back and forth. Completely predictable. But there is a set of non-zero measure trajectories such that if it hits this directly, it comes back. But if it hits here, it goes off. And if it hits on this side, it goes off on this side. And the future becomes exponentially separated from the past. So an infinitesimal change in the initial condition is enough to produce this because of this defocusing effect of this convex boundary. And this system is chaotic. In fact, you can compute the rate at which this becomes exponential.
So that
Due to
can
this-
hold even if there is a circle inside your big circle.
If it's off-center, yes. Then it breaks this angular momentum in waves. But if it's plunk in the middle, then it doesn't.
It's still able to take
Then it's in an annulus and the angular momentum is still conserved. In any case, if you give me the initial angular momentum of this object, and you would have seen these little things with nails everywhere and these threads to make an envelope curve. So it's clear that given a certain angular momentum, the trajectory will never come closer because the velocity doesn't change. It will never come, the speed doesn't change. It will never come closer than the distance of closest approach in one trajectory. It will never come back. And then as time goes along, there will be a little envelope curve formed. So you could put a scatterer and then nothing will happen.
So what is happening in this, when you are taking this box inside,
Yeah.
outside the circle thing, and when there is a circle outside the circle, there is an annular type of thing,
Yeah.
then the particle when will beat in like this previous one,
Yeah.
then they should generate some chaos. Why not they are generating?
Because there is still rotational invariant, there is still circular symmetry in this problem if it's concentric. And there are 2 constants of the motion, immediate constants. It's still circular. The moment it's off-center, you're right. And of course, if it's a second particle, it's always, most of the time, off-center. And then there's chaos. It doesn't necessarily follow that in the stadium problems are very interesting. People have studied this in great detail, both classically and quantum mechanically. The moment you break the symmetry, you lose integrability. That's the whole point. In fact, in this kind of stadium problem, it's not necessary that you should have always a defocusing effect. Other effects could also play a role. For instance, suppose you took... Yeah. Sorry. Yeah, this is like a defocusing effect, right? I mean, it's a convex mirror, so it's defocusing. The rays are diverging out of it. But you could have the other thing also. You could take an arc of a circle, another arc of a circle, and a third arc of a circle, form a spherical triangle out of this. Then, in this stadium, inside this region, typically you have, once again, chaotic behavior. Although there would be sets of periodic orbits of this kind, in general, generically you have chaotic behavior. But both these, you would say, are convex surfaces. Therefore, there is exponential separation. I haven't defined chaos, but I'm just jumping the gun to say that this is irregular behavior. But you could have the following possibility. Take this, take a circle, which is integrable, split it in two, separate them, and then join them by straight line segments. So you have rectangle, and then the slopes match at this point, but the curvatures don't, and you have this. So as long as the ratio of this length to the radius of this circle is non-zero, you have chaotic behavior. There are lots of trajectories where it would bounce back and forth between this, or between this and this, or even in more complicated patterns. But in general, you would have chaos in this system. This is called the Bronimovich stadium.
What if it's an ellipse?
Pardon?
What if it is an ellipse?
Pardon? It's not an ellipse. It's not an ellipse.
No, if it is an ellipse, will it be...
If it's an ellipse, will there be symmetry? Will there be integrability? If it's an elliptic,
Should be...
yes. Yes. You have symmetry in bipolar coordinates now. So you can go to another coordinate system in which the system becomes integrable. Easy to see. So this is certainly true. Yeah. Yeah.
Those two surfaces are sort of focusing surfaces, right? So why can't
Yes.
you imagine that two
Very good question.
those things will actually...
Yeah. There's another spherical aberration here. There's astigmatism. So this is convex lens give you aberration, one kind of aberration. This is a ray optics that's being done. So there's another kind of thing here. The point is at these points, although the slope is the same, the curvature changes. And that is enough to produce this behavior. So that was a non-trivial result due to Bronimovich, which was a Sinai student many years ago discovered this. Yeah. So he actually computed the Hamiltonian as we learned. So as long as this length to the radius of this is non-zero, you have chaos. So this is a sort of minor industry to find out what goes on, and then people put free quantum mechanical particle inside here and ask what happens to the wave functions, etc. It's not integrable, but you have these famous scars in the wave functions and then various properties of the energy levels and so on. So there's a big flourishing industry studying stadia arrays. When should I stop? So I'll come back to Hamiltonian systems next time, and then we will talk about the integrability criteria. The next thing after seeing a little bit about constants of the motion is to ask the earlier question, what happens if you cannot do rectification? What happens if you're not able to do this linearization at all? So now let's go back to x dot equal to f of x. And let's look at trajectories in the vicinity of a critical point. So let x equal to x bar be the critical. In other words, f of x bar equal to 0. An isolated critical point. Then this linearization program fails. And this rectification program fails altogether. What should I do now? Well, again, to solve this equation in the vicinity of this thing, I do a Taylor series. So this is equal to, approximately equal to f x bar, which is 0, plus x minus x bar well, it's the other way around, plus delta f delta x at x bar on x plus higher orders. This is a Taylor series in many variables. This guy here is the Jacobian matrix at that point. And I'm going to start by assuming that that doesn't vanish, that this Jacobian matrix doesn't disappear. It's an n by n matrix formed by differentiating the components of x with respect to the components of x and evaluating it at the critical point. So this is typically what happens. And if this is not 0, it's some constant matrix of some kind. So let's change variables. Let's put u equal to x minus x. Then this equation here, to first order, becomes a completely trivial equation. U dot is approximately equal to L U. It's L. In a sufficiently small neighborhood of this critical point, this is what the equation looks like. And it's a linear equation with constant coefficients here. So we can solve that problem in a sufficiently small neighborhood. How small, I don't tell you at the moment. What's the solution? But it must depend on the initial condition.
U0 times
Well, that's an n by n matrix. This is the column vector. You have to operate on U0, right? So the order matters once you have more than one component. So that's the solution in a sufficiently small neighborhood. Therefore you solve for x. But now in contrast to what happened in the rectification theorem, where things essentially went linearly in time, you got this exponential behavior with this guy sitting here. Now what's the meaning of this exponential of the matrix? It's a series, right? By definition, the exponential map is always defined into LT is summation r equal to 0 to infinity, LT to the top. When does it converge? When does the ordinary exponential series converge? The radius of convergence is infinite. So So mod z less than infinity. Except at the point at infinity, it converges everywhere. What do you call such a function? No, it's much more than analytic. It's much more. It's an entire function. It's got to have a singularity at infinity. It's got to, otherwise by Liouville's theorem you have a